Hello, good morning everyone. Myself Darshan BD, Assistant Professor, Department of ECE, SJBIT. So today we are going to discuss the Module 2. Module 2 is Oscillators and Operational Amplifiers. So here some textbooks. In the Module 2, so it consists of the oscillators and operational amplifier content. In the oscillator, we are going to discuss the Barkhorsam criterion, sinusoidal and non-sinusoidal oscillations, ladder network oscillator, Wien bridge oscillator, multivibrator, single stage astable oscillator, and crystal controlled oscillator. In the second part, we are going to discuss operational amplifiers. In operational amplifier, we are going to discuss operational amplifiers parameters, operational amplifier characteristics, operational amplifier configuration, operational amplifier application circuits. So like inverting and non-inverting amplifiers, voltage follower, summer, subtractor, integrator, differentiator. So consider the oscillator part in that the condition for oscillation that we can consider as Barkhorsam criteria for oscillations. Here, an oscillator is a circuit which basically acts as a generator. Generally, the output signal which oscillates with constant amplitude and constant desired frequency. Means, oscillator is a device that produces continuous and periodic waveform without taking any external input signal. The feedback is a property which allows to feedback the part of the output same as the circuit as its input. Such a feedback is said to be positive whenever the part of the output that is fed back to the amplifier as its input is in phase with a voltage gain A. So we can show it in the figure. We are considering here this is the amplifier. We are going to apply the input. We are going to take the output. Some portion of the output we are going to fed back to input. That is frequency selective network. We are going to consider a feedback network. There we are considering a feedback ratio beta. Here the amplifier gives 180-degree phase shift. Similar way, this feedback network will give 180-degree phase shift. Negative feedback can be applied to an amplifier which is preservably control the gain. Similarly, positive feedback can be applied to oscillator wherever the output is fed back in such a way as to reinforce the input. An oscillator does not require an external signal either to start or maintain energy conserve process. Okay, consider that here in the oscillator we are not giving any input. It keeps producing an output signal as long as DC power supply is connected. That so still it's continuous. The waveform is generating. Assume that sinusoidal input signal Vs is applied to the circuit. As amplifier is non-inverting, the output voltage V0 is in phase with the input signal Vs. The part of the output is fed back to the input with the help of feedback network. No phase change is introduced by the feedback network. As the phase of the feedback signal is same as that of the input applied to the feedback is called a positive feedback. The closed loop gain of a positive feedback is given by AF is equal to A divided by 1 minus A beta. A indicates the voltage gain, beta indicates the feedback ratio. Without any input, the output will remain continuous to oscillate whose frequency depends upon the feedback network or the amplifier or both. Such a circuit is called as an oscillator. Consider the condition for oscillation. You can call it as Barkhousam criteria for oscillation. Oscillator is a device that generates continuous and periodic waveform without taking input signal. The condition for the oscillations are the feedback must be positive. That you can call it as the total phase shift around a loop as the signal produced from the input to the amplifier. The feedback network backs to the input again, completing a loop is precisely 0 degree or 360 degree or a course or integral multiply of 2 pi radians. So overall we can call it as, that is, feedback must be positive, the phase shift must be 0 degree or 360 degree. Second one is the overall voltage gain must be greater than 1. You can call it as overall loop voltage gain. The magnitude of the product of the open loop gain of the amplifier and the feedback factor beta is unity, that you can call it as A into beta. A is the amplification factor, beta is the feedback ratio. That magnitude is equal to 1. The amplifier's gain must be sufficient to overcome the losses associated with any frequency selective feedback network, that you can call it as A into beta is equal to 1. The A is gain of the amplifier. The gain of the amplifier should be greater than 1, and beta is the gain of feedback network. The beta should be less than 1. So to create an oscillator, we need simply an amplifier with a sufficient gain to overcome the losses of the network that produce the positive feedback. So straight away we can say that the Parkinson criteria for sustained oscillation, we are having two conditions. One should be the total phase shift should be 0 degree or 360 degree. The second one is the overall loop voltage gain must be greater than 1. Next one, the classification of oscillator. Electronic oscillators may be broadly divided into the two groups. One is sinusoidal oscillator, or you can call it as harmonic oscillator. Second one is non-sinusoidal oscillator. Sinusoidal oscillator which produce an output having sine waveform. Oscillators basically converts unidirectional current flow from a DC supply into AC waveform of a desired frequency. As described by its circuit component, sinusoidal oscillators operate in the linear region. Considering in the sinusoidal oscillator. Consider non-sinusoidal oscillators. They produce an output which has the square, rectangular, sawtooth waveform as its of pulse shape. So this non-sinusoidal oscillator is also called as relaxation oscillator. In this non-sinusoidal oscillators circuit, voltage or current changes abruptly from one value to another, which continuously to oscillate between these values as long as the DC power supply is applied, this power supply is present in the circuit. Relaxation oscillator or non-sinusoidal oscillators operate in non-linear region of the characteristics. Consider damped and undamped oscillation. Sinusoidal oscillation produced by oscillator may be damped and undamped. So consider that in the sinusoidal oscillation, we are considering damped oscillation and undamped oscillation. What do you mean that damped and undamped oscillation? Oscillations whose amplitude keeps decreasing or decaying with time are called damped or decaying oscillators. The waveform of such oscillator, you can show it in the figure. So you can observe here, as time goes, that the amplitude is reducing. So you can consider that the amplitude, the starting the wave, that A to minus A, so when it goes, the time goes, that the amplitude is decreasing. The subject still oscillates sinusoidally, but that the amplitude is reducing. Amplitude decreases within the envelope of the decaying exponentially. These are produced by those oscillator circuit in which I square R losses, I current and the resistance losses takes place continuously during each oscillation without any arrangement for compensating the same. Ultimately, the amplitude of the oscillator decaying or delaying or reducing to zero when there is not enough energy to supply circuit losses. The frequency or time period remains constant because it is determined by the circuit parameters. Consider undamped oscillation. As we have discussed already, that damped oscillation, in the damped oscillation, as time goes, the amplitude of the signal is decaying or reducing. Okay, in undamped oscillation, oscillation whose amplitude remains constant, that is, does not change with the time, are called undamped oscillation. These are produced by those oscillator circuit which have no losses, or if they have, there is the provision for compensating the losses. The constant amplitude and constant frequency sinusoidal waves you can observe in the figure in the waveform. So this is the example for undamped oscillations. You can observe that the constant, the amplitude and the time you can observe are called carrier waves and are used in communication transmitters for transmitting a low frequency audio information to far off places. So when you are going to transfer the information to the long distance, so we are considering this. When you are going to transfer, we are going to consider the constant amplitude and constant frequency in the undamped oscillation. With respect to the damped oscillation, as time goes, the amplitude of the signal is reduces. But in the undamped oscillation, as time goes means consider that time goes also the frequency and the amplitude is constant. Consider types of oscillators, considering the ladder network oscillator, also called as RC ladder oscillator. Here a simple phase shift oscillator based on three-stage RCR ladder network you can observe in the figure. RC phase shift oscillator consists of BJT amplifier. So BJT is bipolar junction transistor amplifier and three RC sections of phase shift network as feedback circuit. TR1 transistor 1 operates as a conventional common emitter amplifier staged with R1 and R2 and providing a base bias potential, and R3 and C1 provides emitter stabilization. Here we are going to use R1 and R2 is providing a voltage divider biasing. To biasing the transistor, we are going to use R1 and R2 resistor. The total phase shift provided by RC ladder network is 180 degree. at the frequency of oscillation. So how we are going to consider means one RC pair. When you are going to consider one resistor and one capacitor, one RC pair will give 60-degree phase shift. To get 180-degree phase shift, we are using three pair of RC we are using. So three pair of RC. This is the feedback part. This gives 180-degree phase shift. Then the transistor gives 180-degree phase shift. So you can observe that the transistor provides 180-degree phase shift and the feedback part or RC network gives 180-degree phase shift. So to get the 360-degree or 0-degree phase shift, to get the sustained oscillation, this is one of the parameter to get the sustained oscillation. You know that some particular frequency f0, the phase shift is each RC section is 60-degree, so that the total phase shift produced by the RC network is 180-degree. The output of the amplifier is connected to feedback network and the output drives the amplifier. So the conditions for the oscillation in the ladder network oscillator is BJT amplifier produces 180-degree phase shift, RC feedback network produces another 180-degree phase shift. As a result, phase shift around the entire loop is 360-degree. The second one is if A is the gain of the amplifier, we know that A we are considering the gain of the amplifier, and beta is the gain of the feedback circuit. Beta is the gain of the feedback circuit. Then loop gain is A into beta should be equal to 1. This is also one of the parameters to get the sustained oscillation. For oscillators to occur, the beta, the value should be greater than 1 by 29. That means the losses associated with the ladder network is 29. Thus the amplifier must provide a gain of at least 29 in order for the circuit to operate. So that we are considering. So you can observe in the figure. So we are going to apply only that VCC supply. We are not giving any input here. Okay, only we are using that R1 and R2 for biasing the transistor. So three pairs of RC network we are going to use. Then we are going to take the output at the collector point. The R3 and C1 we are going to use to stabilize the emitter part. At the collector terminal of the amplifier, the sinusoidal waveform can be obtained as an output. The frequency of sustained oscillations in the figure is depend on the R and C value. If you are going to vary R and C values, we can get the different frequency. Okay, that's why we are considering that the frequency equation f is equal to 1 divided by 2 pi into root 6 into RC. R and C are the components used in the ladder network. So 2 pi, 1 by 2 pi into root 6. So considering this, the ladder network oscillator, we are having some advantages and disadvantages of this network. Advantages of the RC ladder oscillator can produce audio frequency range. RC ladder oscillator can produce audio frequency range. So we can use for audio frequency range. Disadvantage of this ladder network is the frequency stability is poor. So due to effect of temperature, the component aging. So when you are going to use the resistor and the capacitor, okay, so the temperature will depend on the component. When the resistance gets heated, the resistance value may be changed. Okay, so due to this component aging also, so we cannot get the frequency stability. So after some days, after some years, after some time, the frequency is fluctuating. So consider an example. Determine the frequency of oscillation of a three-stage ladder network oscillator in which the capacitor C value is 10 microfarad and resistance is 10 kilo ohm. So you know that the given values are C and R. C value is 10 micro nanofarad, R is 10 kilo ohm. So using the formula F is 1 by 2 pi root 6 into RC. So you can give that value, you can substitute that C value 10 nanofarad and then 10 kilo ohm, so that you can substitute. So you can simplify that. The final frequency value you are going to get is 647 hertz. That is the frequency obtained from this ladder network oscillator. So when you are going to vary that C and R value, so we can increase the frequency or we can decrease the frequency value depending on R and C value. Okay, so thank you.